NASA has recently made a critical decision that will shape the future of human exploration beyond our solar system. Engineers at NASA's Jet Propulsion Laboratory are systematically turning off instruments aboard the twin Voyager spacecraft to extend their operational life into the 2030s. These twin spacecraft, launched in 1977, remain our only eyes and ears in interstellar space. As Suzanne Dodd, Voyager project manager at NASA, eloquently puts it, the Voyagers have been deep space rock stars since launch, and we want to keep it that way as long as possible. In this video, we will explore the current status of these pioneering spacecraft, examine NASA's power conservation strategy, and discover why these aging explorers remain so scientifically valuable as they journey farther into the unknown reaches of our galaxy. The Voyager spacecraft represent one of humanity's greatest engineering achievements, continuing to function far beyond their intended lifespan. These twin explorers have journeyed farther from Earth than any other human-made objects, with Voyager 1 currently at a distance of approximately 15 billion miles from our planet, and Voyager 2 trailing at about 12.5 billion miles. At these vast distances, radio signals from Earth take over 22 hours to reach Voyager 1 and nearly 19 hours to reach Voyager 2, creating unprecedented challenges for mission controllers. Both spacecraft have achieved the historic milestone of crossing the heliopause, the boundary where the sun's influence ends and true interstellar space begins. Voyager 1 made this crossing in August 2012, becoming the first human-made object to enter interstellar space. Its twin, Voyager 2, followed in November 2018. This achievement was verified using data from instruments, including the cosmic ray subsystem on Voyager 1, one of the very instruments now being shut down to conserve power. The original mission of the spacecraft focused on planetary exploration, with both Voyagers conducting close flybys of Jupiter and Saturn. Voyager 2 continued on a grand tour that also included Uranus and Neptune, taking advantage of a rare planetary alignment that occurs only once every 176 years. These encounters revolutionized our understanding of the outer planets, discovering new moons, rings, and atmospheric features that had never been observed before. After completing their planetary missions in the 1980s, the spacecraft entered the Voyager interstellar mission phase. During this extended mission, they've been studying the outer reaches of the solar system, including the heliosphere, the bubble of charged particles from the sun that surrounds our solar system, and now the interstellar medium beyond it. The data they've collected has fundamentally altered our understanding of the boundary between our solar neighborhood and the rest of the galaxy. The Voyager spacecraft were built with remarkable durability in mind, but even the most robust technology has its limits. Each spacecraft carries identical suites of scientific instruments, though not all remain functional after 48 years in the harsh environment of space. Both spacecraft have endured radiation, micrometeoroid impacts, and the extreme cold of deep space, yet continue to operate and communicate with Earth. Their resilience stands as a testament to the engineering principles of the 1970s, built to last, with redundant systems and robust design. The current scientific focus of the mission centers on gathering unprecedented data about the interstellar medium, the matter and radiation that exists between star systems. This includes measurements of magnetic fields, cosmic rays, and charged particles that cannot be studied from Earth or even from within our solar system. These measurements provide crucial insights into the structure of our galaxy and the conditions that exist between stars, helping scientists understand the cosmic environment in which our solar system exists. Despite their age and distance, both Voyagers continue to make new discoveries. For instance, in 2019, Voyager 2's instruments detected unexpected changes in plasma density at the boundary of interstellar space, challenging existing models of the heliosphere. The Voyager spacecraft face a fundamental challenge that no amount of brilliant engineering could permanently solve: diminishing power. Each spacecraft relies on a radioisotope thermoelectric generator, RTG, for electricity, which converts heat from the natural decay of plutonium-238 into electrical power. These power systems were revolutionary when the Voyagers launched, but the inevitable decay of radioactive material means they produce approximately 4 watts less electricity each year, forcing NASA to make increasingly difficult decisions about power allocation. On February 25, 2025, NASA engineers made the calculated decision to deactivate Voyager 1's cosmic ray subsystem experiment. This instrument, consisting of 3 telescopes designed to detect high-energy particles from various sources in space, played a crucial role in confirming Voyager 1's passage into interstellar space in 2012. The decision to turn off this historic instrument wasn't made lightly, but represents a strategic trade-off to extend the overall mission's lifespan. Following this, on March 24, 2025, NASA plans to shut down the low-energy charged particle instrument aboard Voyager 2. This instrument measures various ions, electrons, and cosmic rays originating from both our solar system and the wider galaxy. Together, these shutdowns present a significant reduction in the spacecraft's energy consumption, potentially adding years to their operational lives. This isn't the first time NASA has had to make such decisions. In October 2024, engineers turned off Voyager 2's plasma science experiment, which measured the flow of plasma ionized gas in interstellar space. That instrument had already been collecting limited data in recent years due to the orientation of Voyager 2 relative to the plasma flow. Even earlier, Voyager 1's own plasma science instrument stopped working correctly in 1980 and was completely shut down in 2007 to preserve power. The power management strategy employs a careful hierarchy of priorities. Mission-critical systems, those necessary for basic spacecraft operations, maintaining correct orientation and communication with Earth, receive the highest priority. Scientific instruments are prioritized based on their uniqueness and potential scientific return, with preference given to measurements that can only be taken in interstellar space and cannot be duplicated by Earth-based instruments or other spacecraft. Each RTG on the Voyagers initially produced about 470 watts of electricity at launch in 1977. Today, they generate less than half that amount, with current power levels hovering around 208 watts for Voyager 1 and 214 watts for Voyager 2. Every watt saved is crucial. The spacecraft require minimum power, thresholds for heating to prevent instruments from freezing, communications and attitude control to keep their antennas pointed toward Earth. The engineering team at JPL employs creative solutions to maximize the remaining power. They've developed sophisticated power-sharing protocols that allocate electricity based on changing priorities and needs. In some cases, instruments are cycled on and off, rather than operated continuously. Heaters for non-essential components have been turned off, allowing those components to operate well below their design temperature ranges. A risky but necessary strategy that has so far proven successful. With the latest instrument shutdowns, NASA projects that both Voyagers will maintain 3 operational instruments through 2025, dropping to 2 in 2026. The hope is that at least one instrument on each spacecraft will continue functioning into the 2030s, allowing the Voyagers to collect unique scientific data for nearly 6 decades after their launch. The strategic power conservation efforts by NASA engineers aim to extend the Voyager mission well into the 2030s, potentially allowing these venerable spacecraft to reach the remarkable milestone of 60 years in operation. This timeline is particularly significant because it would enable the Voyagers to explore regions of interstellar space that may contain different properties than those they currently traverse, potentially revealing new insights about the structure of our galaxy and the interstellar medium. Recent developments with the Voyager spacecraft highlight both the challenges and triumphs of managing such distant explorers. In a remarkable feat of engineering ingenuity, NASA successfully recovered communication with Voyager 1 in March 2023 after experiencing a significant anomaly. Engineers restored functionality by activating a backup transmitter that hadn't been used since 1981, demonstrating the remarkable foresight of the original mission designers, who built in multiple redundancies that would prove valuable decades later. The unique scientific value of the Voyager mission cannot be overstated. These spacecraft provide the only direct measurements of the interstellar medium, the material between stars in our galaxy. This includes data on magnetic fields, cosmic rays, plasma densities, and charged particles that simply cannot be obtained from Earth-based observatories or even from spacecraft within our solar system. As Patrick Conn, Voyager program scientist, notes, every bit of additional data we have gathered since then is not only valuable bonus science for heliophysics, but also a testament to the exemplary engineering that has gone into the Voyagers. One of the most anticipated future discoveries could come from detecting changes in the interstellar medium as the spacecraft move farther from the influence of our Sun. Scientists theorize that at greater distances, the Voyagers might encounter regions of space with different densities, temperatures, or magnetic field configurations than those observed thus far. Such discoveries could revolutionize our understanding of the structure of the Milky Way galaxy and provide context for understanding other stellar systems. The Voyagers also serve as pathfinders for future interstellar missions. The data they collect on radiation environments, dust concentrations, and other hazards helps engineers design the next generation of spacecraft intended to explore beyond our solar system. The New Horizons spacecraft, which flew past Pluto in 2015, is following in the Voyager's wake and will eventually reach interstellar space, though it will take a different path through the galaxy. Beyond their scientific value, the Voyagers carry with them the famous golden records, phonograph records containing sounds and images selected to portray the diversity of life and culture on Earth. These artifacts, intended for any intelligent extraterrestrial life that might find them, represent humanity's message to the cosmos and will likely outlast most other human creations, potentially surviving for billions of years in the emptiness of interstellar space. Linda Spilker, Voyager project scientist at JPL, captures the excitement and uncertainty of the mission's future. Every minute of every day, the Voyagers explore a region where no spacecraft has gone before. That also means every day could be our last, but that day could also bring another interstellar revelation. This sentiment reflects the pioneering spirit that continues to drive deep space exploration, pushing boundaries, accepting risks, and embracing the unknown in pursuit of knowledge. The Voyager mission continues to defy expectations, pushing the boundaries of what was thought possible for spacecraft longevity. As both probes venture deeper into uncharted interstellar territory, they're revealing surprising new phenomena that challenge our understanding of the galaxy. Recent data from Voyager 1 suggests the interstellar medium may be far more turbulent than scientists predicted, with unexpected fluctuations in cosmic ray intensity and plasma density. This turbulence appears to increase with distance from the Sun, hinting at complex interactions between our solar system's protective bubble and the true interstellar environment. One of the most remarkable aspects of the Voyager's ongoing journey is their ability to detect the faint but persistent hum of interstellar plasma, a constant vibration in the charged particles between stars that was completely unknown before these measurements. This discovery, made possible by the spacecraft's plasma wave instruments, provides scientists with a new way to study the density and structure of interstellar space. The hum appears to be caused by the collective motion of electrons in the plasma, creating a faint but detectable oscillation at frequencies too low for most instruments to measure. NASA engineers have developed innovative new techniques to keep the aging spacecraft operational. In 2023, they successfully implemented a software update transmitted across billions of miles to optimize the spacecraft's power usage. This remote tune-up allowed mission controllers to reduce energy consumption by carefully timing when certain instruments take measurements and when they remain dormant. The update was particularly crucial for Voyager 2, which had been experiencing more rapid power decay than its twin. The spacecraft's thrusters, originally designed for course corrections during their planetary flybys in the 1970s and 80s, have taken on new importance in interstellar space. Engineers now fire these thrusters in minute pulses, sometimes lasting just milliseconds, to keep the spacecraft antennas precisely pointed toward Earth, despite the constant buffeting from interstellar particles. These delicate maneuvers require extraordinary precision, as even tiny errors in pointing could make communication impossible across the vast distances. Perhaps most astonishing is that some of Voyager's instruments continued to function, despite operating far beyond their intended temperature ranges. As power conservation has required turning off most heating elements, certain components now operate at temperatures around negative 79 degrees Celsius or negative 110 degrees Fahrenheit, far colder than their original design specifications. Yet they continue returning valuable data, a testament to the robust engineering of the 1970s. The Voyager's longevity has created unexpected opportunities for scientific collaboration. Astronomers now combine Voyager's in situ measurements with observations from Earth-based telescopes and newer space observatories like the James Webb Space Telescope. This multi-pronged approach allows scientists to compare direct sampling of interstellar space with remote observations of similar environments around other stars. As the spacecraft continue their outward journey at about 17 kilometers per second, 38,000 miles per hour, they're approaching a region where the influence of other stars may become detectable. Scientists speculate that within the next decade, the Voyagers might begin sensing the subtle gravitational and magnetic effects of nearby stellar systems, potentially providing our first direct measurements of how our solar system interacts with its galactic neighborhood. Each new day of operation brings the potential for groundbreaking discoveries. The Voyagers have already fundamentally changed our understanding of the solar system's boundary and the nature of interstellar space. As they continue their lonely journey among the stars, these intrepid explorers remind us of humanity's capacity to reach beyond our cosmic backyard and touch the unknown. Their enduring legacy will inspire future generations of interstellar missions, even as they themselves fade into the darkness, carrying our message to the stars. The Voyager twins are now entering a fascinating new phase of their epic journey, where they're detecting subtle but significant changes in their environment. Recent telemetry shows both spacecraft are encountering increasing concentrations of interstellar dust particles, tiny fragments of material from ancient supernova and other cosmic events. These microscopic time capsules, barely a micron in size, are bombarding the spacecraft at velocities approaching 20 kilometers per second, creating detectable electrical signals when they impact Voyager's still-functioning plasma wave detectors. Scientists are particularly excited because this dust appears chemically distinct from material found within our solar system, offering clues about the elemental composition of our galactic neighborhood. Communication with the Voyagers has become an extraordinary technological ballet. The Deep Space Network antennas used to contact the probes have undergone multiple upgrades since 1977, with the most recent enhancement in 2023, allowing for more efficient data compression. This lets engineers squeeze more science from each precious bit transmitted across the growing void. The signal strength from Voyager 1 is now about 20 attawatts, 20 times 10 to the minus 18 watts, by the time it reaches Earth, so faint that the amount of energy collected by DSN antennas in one day couldn't power a LED light for a single second. Yet NASA's receivers can still extract meaningful data from this whisper of a signal. An unexpected discovery came in late 2023, when both spacecraft detected brief but intense bursts of cosmic ray activity lasting just hours or days. These interstellar squalls appear unrelated to solar activity and may represent localized disturbances in the galactic magnetic field. The phenomenon has astrophysicists particularly intrigued because it suggests the interstellar medium isn't as uniform as previously believed. Some theorists speculate these could be echoes of ancient stellar explosions or the wakes of passing interstellar objects, though the exact cause remains mysterious. The spacecraft's power situation has entered a critical phase. Plutonium-238 in the RTGs has decayed to the point where engineers must now make difficult choices between keeping heaters on for certain components or collecting additional scientific data. In a clever workaround, mission planners have begun using the spacecraft's own waste heat to warm key systems, essentially letting the still-functioning electronics help keep each other operational. This delicate thermal balancing act has added months, possibly years, to the mission's lifespan. Remarkably, some of Voyager's instruments are now being used in ways their designers never imagined. The ultraviolet spectrometer, originally intended for planetary atmospheres, is detecting the faint glow of interstellar hydrogen and helium. The cosmic ray detector, designed to study solar system particles, is now providing our best measurements of galactic cosmic rays unaffected by the sun's influence. Even the spacecraft's radio system has become a scientific instrument. By analyzing subtle changes in signal characteristics, scientists can infer properties of the interstellar plasma the signals pass through. The Voyager's journey has also provided unexpected insights about the shape of the heliosphere. Data suggests this protective bubble surrounding our solar system may be more irregular and dynamic than the smooth, comet-like shape long depicted in textbooks. Recent measurements indicate it might resemble something more like a deflating beach ball with dents and bulges created by the interplay of solar and interstellar magnetic fields. This discovery has forced a re-evaluation of how all star systems might interact with their galactic environment. As we continue to receive data from these intrepid explorers, each transmission carries the potential to rewrite our understanding of the galaxy. The Voyagers have become cosmic laboratories studying fundamental physics in an environment impossible to recreate on Earth. Their observations of how particles behave in pristine interstellar space are testing theories about plasma physics, cosmic ray propagation, and the very nature of matter in our galaxy. Even after nearly half a century, these grand old explorers continue to open new windows into the universe around us. The Voyager mission has recently entered what scientists are calling its twilight phase, where every day of continued operation feels like a small miracle. In 2024, engineers noticed an intriguing anomaly. Both spacecraft are experiencing slightly less drag from the interstellar medium than predicted. This unexpected finding suggests there may be fundamental gaps in our understanding of how matter is distributed in our local galactic neighborhood. Some theorists speculate this could indicate the presence of a previously unknown void region with lower particle density, possibly created by an ancient supernova shockwave that cleared out material millions of years ago. One of the most surprising recent discoveries came from analyzing decades of accumulated cosmic ray data. Scientists have identified a curious 11-year modulation in certain interstellar cosmic ray intensities that appears to loosely correlate with the Sun's activity cycle, even at the Voyager's vast distances. This revelation has overturned previous assumptions that the solar influence completely disappears beyond the heliopause. The finding suggests our Sun's magnetic reach extends much farther into the galaxy than anyone suspected, potentially affecting how we model the interaction between stars and their interstellar environments. The spacecraft's aging computers continue to astound engineers. In 2023, Voyager 1's flight data system began showing signs of memory corruption that threatened to end the mission. In response, NASA engineers dug through 1970s-era documentation and devised a clever solution. They began transmitting memory refresh commands that essentially rewrite vulnerable sections of the onboard computers. This technique, never envisioned by the original designers, has given the spacecraft a new lease on life. The team has even discovered ways to repurpose unused memory regions to store critical engineering data when other systems fail. Thermal management has become an increasingly creative challenge. As power levels continue to drop, engineers have implemented an innovative thermal banking system where they carefully time instrument usage to take advantage of residual heat from recently powered components. For example, they'll schedule plasma wave measurements immediately after the high-energy particle detector operates, using its waste heat to keep the plasma instrument within its operational temperature range. This delicate thermal choreography adds complexity to operations, but has proven remarkably effective at extending science return. The Voyagers are now detecting intriguing variations in the direction and strength of the interstellar magnetic field. Recent measurements show the field orientation changing in ways that don't align with existing models of galactic structure. Some scientists believe this could be evidence of what they're calling magnetic bubbles, localized regions where the galactic magnetic field becomes twisted or compressed, possibly by shock waves from long-ago stellar explosions. These findings are forcing astrophysicists to reconsider how magnetic fields propagate and evolve in interstellar space. Communication with the spacecraft has reached unprecedented levels of precision. The Deep Space Network now tracks the Voyager's positions so accurately that they can detect minuscule velocity changes caused by individual dust particle impacts. This has created an unexpected new science opportunity, using the spacecraft themselves as giant detectors for interstellar material. By analyzing these tiny perturbations in the probe's motion, researchers can estimate the mass and velocity of impacting particles, providing a unique window into the microscopic constituents of our galactic environment. Perhaps most remarkably, the Voyagers continue to serve as valuable technology testbeds. Lessons learned from keeping these antique spacecraft operational are directly informing the design of future interstellar probes. NASA's upcoming interstellar probe mission, planned for launch in the 2030s, will incorporate numerous Voyager-inspired innovations, including more robust radiation hardening, advanced fault protection systems, and flexible power architectures that can adapt to changing mission requirements over decades-long timescales. As the Voyagers press onward into the unknown, they're crossing invisible boundaries we didn't even know existed. Each new data point challenges our assumptions and expands our understanding of what lies beyond our solar system. These resilient machines, built with slide rules and launched before the first personal computers, continue to teach us profound lessons